Hello everyone, my name is Khalil Rashid and welcome to my talk about secure boot for embedded and IoT devices in Embedded Online Conference. We will be covering the following agenda item today. Why cybersecurity is a need for IoT devices. More and more IoT devices coming to the market, more and more potential surface for attack is becoming bigger and bigger. The impact of cybersecurity and EU GPSR regulations. How a secure boot can be the foundation for overall cybersecurity concept. What are the pillars to realize the embedded security? Then I would just deep dive into chain of trust understanding. I would like to, at the end, summarize everything and would like to point you towards my own written white papers related to cybersecurity and secure boot implementation. Okay, what is my background? I'm the founder and CEO of Epteck GmbH in Frankfurt, Germany, and focusing on mostly working on as an embedded Linux Yocto expert, IoT cybersecurity consultant. I had been doing this job since 18 years and have realized in many big projects related to automotive, medical, and consumer items, security, secure boot, and reliable secure remote firmware update solutions. Let's go into cybersecurity in embedded systems. So imagine a simple IoT device. We are adding more and more devices into our home, into our offices, into industry. So Industry 4.0 will be connected devices, and the more and more connected devices means more and more vulnerabilities and more surface for attack is available. So in your imagine that cybersecurity in embedded IoT, how much it have financial impact. That in only in 2028 it was 13.8 trillion US dollar loss. And if you see the graph on the top right side, you will realize that this loss is increasing. This is the reason there should be now focus and spending on the cyber security more. It had been for many years a topic of nice to have, and it's an hidden feature in the product and nobody wanted to realize it. One IoT device which is not cyber security principle compliant and implemented without any secure boot functionalities is prone to bootkits and rootkit attacks. And once a device is being attacked, it actually exposes the complete network. Recently in 2024 there was an incident in US hospitals that there was ransomware attack targeting IoT connected medical devices. They had to actually disconnect all the devices to continue normal operation, but there was a lot of patients that are leaked. And you can imagine from the other chart that the malware percentage, like introducing a wrong code or redirecting the boot process towards a wrong code, had been the biggest cause for the cybersecurity. Let's see how we can minimize this risk. While looking into these attacks and impact of these attacks in our life, EU have implemented some general product security regulations. These general product security regulations defines actually that no product should come to the market, no IoT product should come to the market with known vulnerabilities. This is a very broad term, but now it is getting confined more and more. Non-vulnerabilities means that we should not leave any open ports on the application level. We should not have any. We need to use static code analyzers to not leave the memory leaks. We should not let a device which is prone to attack by putting the rootkits. So the root, the firmware can be and other firmware from outside can be played on the device. So these regulations impact the manufacturers and consumers. This regulation forces the manufacturers to fulfill the guideline and prove that the device is not having vulnerabilities. This regulation had been introduced into the IoT application world from 13 December last year and will be officially enforced on each product, and there will be it will become a standard, and there will be certification based on these regulations for the devices. So from 2027 it will become hard. So currently in automotive and medical devices it's becoming more and more important. Soon it will become more and more important for all other industrial and home appliances domain. Secure boot serves as a foundation for cybersecurity. Imagine you have the best cybersecurity architecture and concept, and you have deployed it. Cybersecurity includes a lot of components. But if our device we can just simply root that device and we just redirect the firmware to a different direction, then all the cybersecurity measures had been wasted. How this happened? Imagine a standard application. For start, on your hardware, you have some kind of middleware, driver, bootloaders. Then here comes the operating system, and on top of operating system, there is application. Just imagine there are 9 essential security considerations for a product, like security for remote firmware updates. So it's a complete domain which need to be implemented in the right way. Secure communication protocol, crypto standards. So every day we are inventing new and new crypto standards. We are enhancing the security for the communication. Access control and permissions, also a big domain. Intrusion detection and prevention, denial of service attack detection, threat modeling and vulnerability management, data privacy and protection. This is also another part of regulation. Regular security testing and assessment from the security body and security specialist. Then the hardware security, it should be anti-tampered. So imagine that all this from 1 to 8, these are the big domains of cybersecurity. Whereas just take a device, you apply all the concepts from 1 to 8, all the security consideration from 1 to 8, and each security consideration is a huge amount of work to be done. Now, on this device, you simply boot an unknown, untrusted firmware. Just bring that firmware into the memory through any mean. The security is not implemented to block the firmware loading onto this device. The device is not locked to not accept any other firmware which is unsigned and untrusted or unencrypted, not coming from the known sources. Then all the first 8 security considerations are not relevant anymore. The moment someone have played just programmed a bootkit onto your device, that moment your device and your whole network of industry or a home or a hospital, everything is on stake. Now the identity can be stolen. Now the credit card information can be stolen. Now your passwords are at risk. So if somebody enter through a door into your home by just putting a home device or industrial device with a bootkit or rootkit, simply all the security doors are broken. So this is the reason why the fundamental component of the cybersecurity is secure boot. Even the hardware security and tampering, mostly this work is done by the vendor, the chip vendors. Now, the secure boot process, which is including root of trust and chain of trust, is the most central and fundamental and essential part of the whole security concept in a device. Let's see how the pillars of a secure boot look like. So secure boot is also not one concept. Okay, it is comprised of multiple components. If we look at the pillars of secure boot, on one side, when a device is powered on, from power on, if you see that see these three pillars, and from the power on to move towards the first bootloader, and from bootloaders to kernel to rootfs and to applications. From power on, when boot ROM takes control of the device, it calls the bootloader. The chip built-in firmware which loads the very early stage bootloader, it must validate the bootloader, then the bootloader validates the kernel, and kernel validates the rootfs, and this actually makes the chain of trust. The root of trust is actually defined at the first very early stage bootloader, and that need a lot of consideration also. So this is a one pillar. When you put a binary onto a device, that binary should be having this chain of trust implementation mechanism in that. But imagine now to create these binaries, that each previous firmware validates the next firmware, you need a PKI infrastructure. So private key signing infrastructure. Private key signing infrastructure is in your server, in your computer, in your DevOps. What does it mean? You have to produce your binaries. After producing the binaries, you need to get them signed with private keys. Those private keys must be secured. So that defines, you need to create a pillar of private key infrastructure, where you are protecting your private keys, even they are not exposed to the all engineers in the project, in the development team. Normally, this is realized by utilizing a HSM module. It's called hardware security module. You can utilize an HSM in cloud. You can utilize a HSM hardware HSM. You can utilize a soft HSM. But at the end, you need some kind of HSM where there are multiple responsible people which allow in changing the key. HSM gives us a mechanism where we can only and only send our binaries which are generated for the bootloader. Like, you just imagine a microcontroller project. You just create a binary, you want to get it signed. So instead that you get the private key into your local computer or into your build machine, you actually send the binary to an HSM, hardware security module, and based on the configuration, which algorithm you want to use for signing, it will utilize the private key, will sign your binary and give it back to you signed binary. Then that signed binary is sent to the hardware and utilized. Now the bootloader on the hardware need to know that this is a signed binary and what is the mechanism to verify it. And normally that mechanism is called chain of trust also. Okay, that how to tell to the chip or to the CPU or any system on chip module that how to put it. If you take the example of IMX, so IMX6, IMX8. On IMX6 or IMX8, we have something called HAB v4, High Assurance Boot version 4. So high assurance boot version 4 actually defines the root of trust, where the chip, the CPU itself, verifies the first stage bootloader, which is in the case of IMX6 and IMX8, it's the SPL, secondary program loader. It is managed by the U-boot project, and that this first stage bootloader and then actually calls the second stage bootloader, which is U-boot. We can discuss a little bit more. The have v4 architecture or infrastructure of IMX or coming from NXP actually becomes the signing tool also for this artifact. So you can sign your first stage bootloaders. You can even sign the second stage bootloader. You can have the signing of the kernel, Linux kernel, and continue. So, but the pillar of protecting the private key is very, very important. Then there is a third pillar to understand. On one side, the device should boot only the trusted firmware. Each previous binary need to validate the next one. We will see this in the next slide also with the diagram. But signing is important, signed images are important. But imagine a situation when you actually are running your device and your device need to do certain communication. It need to connect to maybe a backend server. It could be an HTTPS server, or it could be MQTT server, or it need to connect to some other services in cloud. All of these services have certain way of authentication. These authentications are done with certificates or with tokens, like JWT tokens for Java. For that, you cannot simply put those certificates and keys and tokens into the firmware binary. This can be easily extracted from a binary and can be utilized, and that creates an attack surface for your server. Now, you need to have a kind of secure storage on your device. So those application CPUs based SoCs which exist from Xilinx or from NXP, all of them have certain mechanism to realize. There had been a common way to have the secure store on the device was that use TPM. So TPM are trusted platform modules, which comes in different variants, and they comes with different crypto algorithms. They come with different size of storage, and they work on I2C or SPI interface. If your hardware does not have, the PCB hardware does not have a TPM module, you can actually add a soft TPM. The soft TPM can be created by using OPTE plus plus an area of your eMMC storage or a partition. Normally, the modern eMMC partition also includes a partition which is around 4 megabyte called RPMB, replay protected memory. So you are saved from replayable attacks also. So when you combine RPMB with OptEE, it gives you a secure store. And secure store is something like a cupboard with multiple shelves, and each shelves can have its password, and you can put your tokens and private keys there. The point of having this secure store, the moment you put any key or any token or any kind of you put certain keys and tokens and certificates into this store. These keys and tokens does not leave the secure store. Rather, you receive an encrypted piece of data. You request on your device to this OptEE that please decrypt it, and then you read a key from the secure store, and this token need to be utilized during runtime of the application to authenticate with the backend. That your application program will read the token from OptEE, will utilize it to establish connection. It is never stored inside your rootfs, inside your any kind of persistent storage, in any RAM region. It's just a runtime variable in your application. The moment device is off, it is gone. It was only and only available in the secure store. So this type of mechanism is needed on each device. So a pillar of chain of trust, a pillar of PKI, private key signing infrastructure, and then a pillar of having a reliable secure store on your device. These three pillars all together make as a combination defines a secure boot infrastructure. So two things goes on the device and one thing stay on the backend server in the company. How does this chain of trust works? Chain of trust is defined to be that each previous component is responsible to first validate the next component and then call it or jump it and boot it. So this happens. The chain of trust is starting from the POR. So power on reset. So boot sequence, which is defined for any CPU, starts with a ROM code, execution of ROM code. This ROM code is actually executed immediately after you power on the device. From power on, the ROM code verifies, go and read for the bootloader. When it reads the bootloader, it says, oh, it is signed. I need to take the key from the bootloader and verify its signature. After verifying the signature of the bootloader with its own public key, it simply have to validate again the public key hash, that if this key in the chip OTP, one-time programmable memory, if the PKH, public key hash of that public key of the bootloader is available in PKH and it matches. So each chip have 4 slots of PKH. So these PKH are stored on the bootrom use.pkh slot to validate the bootloader, and once the bootloader is signature is verified, it starts the bootloader after signature verification. Then bootloader starts, and a bootloader have a mechanism that it has the public key of the kernel fit image or the kernel container. So it uses the public key which is built into the bootloader binary, and it verifies the Linux kernel. So bootrom as a first component verified the bootloader with the key. Bootloader is verifying the Linux kernel with another key. The same way we can call that kernel have the hash for the rootfs. So the last block is the rootfs, which actually holds the application, and that is normally a rootfs is a verity protected rootfs. A verity protection means that it is not a single bit can be changed on that. So the kernel verifies the root hash and compare it with the root hash provided inside the kernel for that rootfs and simply start it. This way, from the power on to the application, we reach that each previous component have verified the next component and system is booted. There are a lot more details, but unfortunately we cannot cover in 20 minutes. I would say in the realm of IoT, cybersecurity is not a choice anymore. It's the foundation. A single unsecure device can collapse an entire digital ecosystem. Either it's in the industry, it's a smart city, or it's a home. So cybersecurity is very, very important. IoT without security is like smart home with open doors, intelligent but completely exposed. Want to learn more about it? Please follow my LinkedIn page. I put regular every day some posts related to secure boot, and you will be learning by following 2 minutes at Croissant every day, or you can simply go and download the white papers which I have written about cyber resilience and best practices in secure boot. Thank you very much for your time and patience, and see you in next conference. If you have any question, please post. I'm available.